We'll continue where we left off in our last example. We found that when trying to solve the system of linear equations mechanically, we reached a contradiction. 16 never equals negative 16. We concluded, therefore, that the system had no solution. Now let's think back to what this means conceptually. A system that has no solution means that the two lines never intersect. That means that the lines are parallel. Because there is no point of intersection, there is no solution to the system. The system is said to be inconsistent. And because the lines are distinct, they are different lines, they are still independent. All right, let's look at our next example. X plus 5y is equal to 12, and 2x plus 10y is equal to 24. To use the substitution method, to me, it seems obvious that we should try to isolate the x variable in the first equation. At least that's the simplest thing to do. It's certainly not the only option, but always looking for the fastest route. So if we were to subtract 5y from both sides, we have that x is equal to negative 5y plus 12. In the second equation, that is what we're going to substitute for x. 2 times what x represents plus 10 times y is equal to 24. X represents the quantity negative 5y plus 12. Here we have an equation with a single variable, in this case y. Now let's clean this up a bit. First we'll distribute on the left. Let's combine like terms. On the left-hand side, negative 10y plus 10y is 0. So we're just left with 24 is equal to 24. Once again, our variable has disappeared. However, this is a true statement. 24 always is equal to 24, regardless of our choice for x. That means that there are infinitely many available choices for x, and there are infinitely many solutions. That's not to say that every ordered pair is a solution to the system. It just means that we have an infinite number of choices for x. However, the corresponding y coordinates will have to be calculated for these ordered pairs. What reaching a statement like this means is that regardless of our choice for x, the statement is true. This is what we call an identity. It's a statement that is always true regardless of our choice for the variable. This tells us that there are infinitely many solutions. But be careful, that's not the same thing as saying that every ordered pair is a solution. Think back conceptually to what this could mean. We possibly have two equations that represent the very same line, so that as we try to graph the two lines, we end up tracing over the first one when we try to draw the second one. That means that every point on the line is a point of intersection, and every point on the line is a solution to the system. So the solution takes on a very unique form. The solution set is the set of all ordered pairs x comma y such that, and then we write the condition. We can write either of the two equations as our condition. So in this case, I'm going to write the condition that x plus 5 times y must be equal to 12. This is what we called set builder notation. Because there's no way to list all of the ordered pairs, given that there are infinitely many of them, this gives us a rule for determining which ordered pairs make it into the solution set and which do not. In this case, we do have at least one solution, so the system is consistent. However, because the two equations represent exactly the same line, we say that the system is dependent. Now that we've reviewed how to use the substitution method, let's look at how to use the elimination method, otherwise known as the addition method. The idea behind this method is that we want to be able to combine the two equations into one by adding, with the hopes that one of the two variables will disappear. Sometimes this will happen automatically, and sometimes it does take a little bit of manipulation. For example, if I have x plus 3y is equal to negative 18 and negative 7x plus 4y is equal to negative 24, adding these two equations as they are is not going to eliminate x, and it's not going to eliminate y. Let me show you, and then I'm going to erase this. X plus negative 7x is negative 6x. 3y plus 4y is 7y. Negative 18 plus a negative 24 is equal to a negative 42. So you see that nothing has canceled out. So we're going to need to do some manipulation first. What we're going to do is we're going to choose a variable that we want to isolate. For example, I want to isolate the x variable. In order for us to add those two terms and get 0, the coefficients must be opposite in sign but of the same magnitude. So it would be great if I had a positive 7x in the first equation. Well, turns out I can do that. I can get that to be a positive 7x. I would just have to multiply by 7 on both sides. So if I multiply by 7 on both sides, I get 7 times x plus 3y on the left is equal to 7 times negative 18 on the right. This is going to give us 7x plus 21y is equal to negative 126. Now I have an equation that, when added to the second equation, will eliminate the x variable. So let's copy the second equation exactly as it is. Now when I add these two equations together, I'm sorry, I missed the negative sign here, very important. 7x plus a negative 7x will be 0. 21y plus 4y will be a 25y. And on the right, negative 126 plus a negative 24 will give us negative 150. Now, if I divide both sides by 25, I get that y is equal to negative 6. Now that I have the value of y, I can go back and solve for the value of x. You could do this using either of the two original equations. I'm going to go ahead and use the first equation. So in the first equation, we had that x plus 3 times y is equal to negative 18. Well, now we have found that y is negative 6, so we can substitute that in. Let's go ahead and clean this up a bit. We have x minus 18 is equal to negative 18. Adding 18 to both sides, we find that, I'm going to write that part because I know it can be confusing. We find that x is equal to 0. That's not a contradiction. 0 is a number. It can be the value that x represents. So we see here that we have one solution, and the solution is the ordered pair. 0 for x, negative 6 for y. And because this can be confused with an interval, we're going to go ahead and put the curly brackets around this ordered pair to indicate that this is a set containing one solution, namely the ordered pair 0, negative 6. Again, just to practice with language, because there is a single point of intersection, the system is consistent, meaning there exists a solution. The system is also independent because the two equations represent distinct lines. All right, let's do this again. In the next example, we have to choose which of the two variables to eliminate. Just to be different, why don't we try to eliminate y this time? So we need those coefficients to be opposites of each other. Same magnitude, just opposite sign. That means I'm going to have to multiply both equations in order to get those matching coefficients, but with opposite signs. Think about the least common multiple of 7 and 5, 35. So to get 35 as one coefficient and negative 35 as another, One choice is to multiply the first equation by positive 5 and to multiply the second equation by negative 7. Again, because we're multiplying both sides by the same quantity, the equations are equivalent. So let me write the original left-hand side of the first equation and the original right-hand side of the first equation. Then the original left-hand side of the second equation and the original right-hand side of the second equation. So let's go ahead and distribute. So we have negative 35x plus 35y is equal to, I'm going to have to do this longhand, 7 times 5 is 35, and a 3 would give us 38. In the second equation, we have negative 14 times x minus 35y is equal to negative 287. Now, if I add these two equations together, negative 35x minus a 14x will be a negative 49x. Notice that 35y minus 35y is 0, as we intended. And on the right-hand side, let's just carefully subtract. I think we get positive 98. Now, if we divide both sides by negative 49, we find that x is equal to negative 2. Now we can solve for the corresponding y-coordinate by using either of the two original equations. It's not going to matter which one you choose. Let's just choose the second equation because the numbers are smaller, right? The coefficients are smaller, and the 41 is smaller than the 77. It really doesn't matter. So using the second equation, we have that 2 times whatever x stands for plus 5 times y must equal 41. Well, we found out that x has a value of negative 2. So as we simplify this, we have negative 4 plus 5 times y equals 41. Adding 4 to both sides gets us to 5y equals 45. And then finally, dividing both sides by 5, we find that y must equal 9. So that means that we have a single solution. It is the ordered pair, negative 2 for x, 9 for y. And again, we're going to use the curly brackets to indicate that this is a solution set. Looks like there's a single point of intersection, which means that the system is consistent and independent. All right, let's look at another example. We have 2x plus 4y equals 8, and 4x plus 8y equals negative 16. Doesn't matter which of the two variables to eliminate first. Let's just try to eliminate the x variable first. Well, 2 and 4 are already very closely related. 4 is a multiple of 2. It'd be great if we can get those coefficients to match in magnitude, but be opposite in sign. And I think one way to do that is to multiply the first equation by negative 2. So if we multiply the first equation by negative 2, we'll have negative 2 and negative 2. And we're going to multiply that by 2x plus 4y on the left. And we're going to multiply that by 8 on the right. So we have negative 4x minus 8y is equal to negative 16. Now, let's bring the second equation unchanged and add it to this one. Negative 4x plus 4x is 0. Negative 8y plus 8y is also 0. So it looks like the entire left-hand side is just 0. On the right, negative 16 minus 16, be careful. This is negative 32. Remember that we're adding. Now, 0 is never equal to negative 32. This is a contradiction. That means that the system has no solution. Recall conceptually that if we graph these two lines, they will never intersect. That means that these are parallel lines. Since there is no solution, we say that the system is inconsistent. However, these represent distinct lines, different lines, so the system is independent. Finally, let's look at our fourth example. X plus 5y is equal to 12. 2x plus 10y is equal to 24. In order to use the addition or elimination method, I'm going to multiply the first equation by -2 so that the x coefficients are opposites of each other. So again, I'm going to multiply the first equation by -2. So we have -2 times x plus 5y on the left and -2 times 12 on the right. Distributing, we get that -2x minus 10y equals -24. Now let's bring the second equation unchanged. We have 2x plus 10y equals 24. When we add these two equations, -2x plus 2x, that's 0. -10y plus 10y, that's also 0. So we get 0 on the left. And -24 plus 24, well, that's 0. Notice that this is a true statement this time. 0 does equal 0. In fact, this is always true. This is called an identity. The conclusion that we reach is that there are infinitely many solutions. In fact, if we think back to what this means conceptually, these two equations represent the very same line. That means that the two lines are represented by a single graph, and every point on that graph is considered a point of intersection or a solution. So the solution set can't be written as a list. It must be written in set builder notation. We'll say that the solution consists of all ordered pairs x comma y such that, and then we have to write a condition. You can choose either of the two original equations as your condition. The first one just seems a little simpler, so we'll write that the condition is that x plus 5y must equal 12. If you had chosen the second equation, the solution would still have been represented correctly. It would just appear differently. Again, conceptually, this is a system that does contain at least one solution, so it is consistent. However, the two equations represent the same line, not distinct lines, so the system is dependent.